Hi everyone, and welcome back again. Today we're going to be doing a little bit of practice with inverse Laplace transforms, and we'll continue this in another video with a few more examples. We're just going to get right into it. We're going to try and be pretty careful this time. Next time we'll try to go a little bit quicker and try a couple of tricks to speed things up. But let's get right to it now. So our goal here is to find the function whose Laplace transform is equal to the given thing. And we're going to be doing that by recognizing some of the formulas that we have developed for Laplace transforms. So for this one, we have 3 over s to the fourth, and we'd like to find the inverse Laplace transform of that. So the relevant formula to recall is that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1. So we're going to try to make things look like that. And we're going to take advantage also of the linearity of the Laplace and inverse Laplace transforms. So we have 3 over s to the fourth on the inside here. And we need to make it look like this. So we're going to do that piece by piece. So first of all, s to the fourth is s to the 3 plus 1. So if we want this to match up with the formula that we have over here, then we're going to need to have a 3 factorial here. What we had already was a 3 that we can pull out to the front, and then this will be divided by 3 factorial. So hopefully everything should check out here. This 3 factorial and this one should cancel, so that we're really left with just 3 over s to the 3 plus 1, which is what we had before. All right, and now using the formula, first of all, 3 over 3 factorial is 1/2, and this is the inverse Laplace transform of t to the third. And that's all there is to it. That's our first inverse Laplace transform for today. Okay. All right, so now let's try something with a couple of parts. Here we have the inverse Laplace transform of 1 over s and 1 over s cubed. So we're going to be using similar formulas here, except first we're going to break this up using linearity. This is the inverse Laplace transform of 1 over s minus the inverse Laplace transform of 1 over s cubed. Okay, so take some time now to try and do this yourself, and then come back and see if you agree with my answer. So hopefully pause the video to make that happen. If not, do it now. Okay, and we're back. So what did you get? Well, first of all, we have the inverse Laplace transform of 1 over s. That we should recognize as the inverse Laplace transform of h of t, or of the function 1, which are the same because we're only considering t values that are greater than or equal to 0. And then minus, and this is the inverse Laplace transform of, well, again, it's going to be similar to the kind of thing that we had before. We have the inverse Laplace transform of, well, let's see, it's going to be s2 plus 1 here. If we want to make it match the formula, we need a 2 factorial there. And we had 1, and we're going to divide by 2 factorial. So that having been done, we now have, well, h of t is for all t greater than 0, greater than or equal to 0, which are the only ones that we're looking at. This is just 1. Here we have 1/2, and that's the inverse Laplace transform is t squared. And so we have 1 minus 1/2 t squared for t greater than or equal to 0. Okay, great. Moving on to the next one. Inverse Laplace transform of 3 over s minus 4. So do that one real quick. Should be able to get that very quickly. All right, so this is 3 times the inverse Laplace transform of 1 over s minus 4, which we should recognize as 3e to the 4t. Again, if I never say it, it's always for t greater than or equal to 0. All right, so that was quick. Let's do one that's a little bit more involved. Whoop, come on now. There we go. So the next one, we have the inverse Laplace transform of 5 minus 3s over s squared plus 9. So this we're going to break into 2 parts according to whether we have an s or a constant on the top of this irreducible quadratic. So this becomes 5 times the inverse Laplace transform of 1 over s squared plus 9 minus 3 times the inverse Laplace transform of s over s squared plus 9. Now, looking at our table of Laplace pairs, we should recognize a few things. So first of all, the Laplace transform of sine of omega t is equal to omega over s squared minus omega squared. And the Laplace transform of cosine of omega t is equal to s over s squared, plus omega squared and plus omega squared. So in this case, we're looking at omega equals 3 to match with our format here. Okay, so that means that in order to make our original thing match up, we need to have a 3 on top of this first one, right? Because we have an omega here. To go with the omega squared, we have a 9. That's 3 squared. We need a 3 up top. So we get 5/3 inverse Laplace transform of 3 over s squared plus 9 minus 3 inverse Laplace transform. This one's already in perfectly good form, so we can leave that. And so we get 5/3 sine of 3t minus 3 cosine of 3t. That's our inverse Laplace transform. All right, lastly, one more. In this case, this is something a little bit different. On the denominator here, we have 25 minus s squared, so we don't have the plus in between them, and also the s squared is second, which is a little bit unusual. So we're going to undo that a bit and break this up again in the same kind of way, separating out the parts according to what's in the numerator. So we can rewrite this. We have 10 inverse Laplace transform of s over, and I'm going to reverse the sign here, so I'm going to put sine s squared minus 25, which means I need a minus sign on the outside. Cancel that out. And then similarly, that's going to make this plus 3 inverse Laplace transform of 1 over s squared minus 25. Okay, so what's going on here? Well, now, again, we have to recall a few formulas, and these are maybe a little less familiar because they involve the hyperbolic sine and cosine. So the Laplace transform of the hyperbolic sine of omega, or I guess in the table we call it alpha t, is equal to alpha over s squared minus alpha squared. And the Laplace transform of the hyperbolic cosine of alpha t is equal to s over s squared minus alpha squared. Now, these are entertainingly called sinh and cosh. These are the hyperbolic sines and cosines. I've talked about this in a previous video. Worth looking up the definition of those. We're going to use them in just a second. But here, if we look at what we have, if we just let alpha equal 5, then this will match up with the two formulas that we have above. Almost. The only thing we need to do is get an appropriate number above the s squared minus 25 in the second term. So, for example, here we have minus 10, and this is exactly the inverse Laplace transform of the hyperbolic cosine of 5t. And then we have 3 inverse Laplace transform of, let's clean that up a little bit, of 5 over s squared minus 25. But to put the 5 in there, of course, we have to divide by 5 on the outside. And so that becomes minus 10 cosh 5t plus 3/5 sinh 5t. All right, so that's the answer. You can leave it absolutely like that, but if you're not, a little bit unfamiliar with those things, let me just review what those are. So that's minus 10 times, this is e to the 5t plus e to the minus 5t over 2. And then this other one, sinh, is sinh of 5t is e to the 5t minus e to the minus 5t over 2. So we could rewrite this as minus 5 times e to the 5t minus 5e to the minus 5t plus 3/10 e to the 5t minus 3/10 e to the minus 5t. So if you really want it to be in terms of exponentials, it would be, let's see, minus 4.7 e to the 5t minus 5.3 e to the minus 5t. Now, an alternate method of doing this would have been to use partial fractions. You use partial fractions, right? Recognizing that s squared minus 25 is s minus 5 times s plus 5. All right, so you could do partial fraction decomposition. You would get something over s minus 5, something over s plus 5, and then you get exactly these exponentials that we're seeing here. So that's an alternate method. Try that out. Make sure that you get the same answer both ways, but I'm not going to do that here in this video. So these are